Hi everyone, myself Guru Gandagude. Today I am explaining the topic of synthesis. Synthesis is a process of converting higher level of abstraction into the lower level of abstractions. Means higher level of language into the machine readable language. There is two types of synthesis. One is logical synthesis and another one is a physical synthesis. In the logical synthesis, we can convert the RTL code into the gate level netlist. In the physical synthesis, we can convert the gate level netlist to the GDS form, layout formation. In a logical synthesis, we will get the gate level netlist that we generated gate level netlist we take and we'll do the layout formation. It's a physical synthesis. Logical synthesis. Logical synthesis is a process of converting RTL code into the gate level netlist. We are given the RTL code and we have to convert to the gate level netlist. It is useful for PNR. So it is a logical synthesis. Goals for logical synthesis. What are the goals? So to get the gate level netlist. So our main goal is to get the gate level netlist from the logical synthesis, and we have to insert the DFT logic. DFT logic is a design for testability. By using the scan flow, we test the logics and logical optimization we have to make. After that, we have to insert the clock getting circuit. Clock getting circuit is used to reduce the dynamic power dissipation. So whenever we required the clock signal, we can on the clock signal. When we are not required, we can off the clock signal. So to get the SDCs, we have to get the SDC also. We have to get, so SDCs contains like clocks, input delay, output delays, and operating conditions, wire load module. These are all helpful for the physical design. So these are all goals. We have to achieve these goals by using logical synthesis. Inputs for logical synthesis. What are the inputs? Like we have to give means RTL code we have to give of the libraries and the constraints. Okay. Here is a synthesis flow. It is full of synthesis flow. We have to do this synthesis by using this flow. So here is develop the SDL file. Here the SDL file is developed and RTL code. That is a SDL file. So after that, develop the SDL file. Specifies a library. We have to specify the library in the DC compiler. After that, we have to read the design. If you have to reading the design, analyze, elaborate, and read file. These are three steps for reading the design. Design environments. We have to set the design environments like operating conditions, wire load module, uh, driving cells, set load, set maximum, minimum library, and set fan out load. This is design environment. Define the design environment. After that, we set the design constraints. We have to set the design constraints like set maximum tension, maximum fan outs, maximum capacitance. These are the design rule constraints. Design optimization constraints are the create clock, set clock latency, set propagation delay, set clock uncertainty. These are all the design optimization constraints. Select the compile strategy. Here we have to select the compile strategy, top down and bottom up. Top down is means compilation of all the blocks at a time, and bottom is we are compiling sub blocks, each blocks. Optimize the design. You have to optimize the design by using compiler, compile ultra. Mainly we will use a compile. Compile ultra if the timing is not meeting, it is violating from little bit values. So we have to use the compile ultra for meeting the timing. Analyze and resolve the design problems. We have to check the our design is correct or not. We have to check the timing. We have to check the constraint paths. We have to check the area. We have to check the power. By these all, we have to, if we are having satisfying, we can resolve the resolve the problems and design. After that, we have to save the design. If we are satisfied with the values, we can save the design and write the SDC for it one, and we have to write the netlist. These two are useful in PNR. This is the output for the synthesis. We will see the in details of the flow. Develop the SDL file. Here the SDL file is developed according to the specification of the customers, and here is the written in the SDL hardware description language. RTL code, register level, register transfer level. What is the specifies the link libraries. Here we are specifying the libraries to the design compiler. Those are link library and the target library. Link library is used to resolve the cell references in our design. And link libraries contain the information like macros library. This is the macros library, standard cells library, technological node, and the threshold voltage. Macros library and standard cells library. Technological node like TSMC 28 nanometer technology and threshold voltage HVT or LVT like this. After that, target library. Target library is used to build or modify the netlist for our design. Target libraries contain the informations like standard cells library, technological node like that only like TSMC 28 nanometer technology, or it will display technological node. What is in the design is having on which technologies, and threshold voltage. What is the voltage? High threshold voltage or low threshold voltage? This will display in the libraries. These all paths. In the past, we will having the standard cells library and the technological load. There is having TSMC 28 nanometer technologies, 9 HVT cells. It is having one path. So it is all about libraries, link library, target library. After specifying the library, we have to read the design by using three stages. In this, analyze, elaborate, and the read file. It is analyze, it is elaborate, and read file. Analyze. Analyze, it will read the SDL source file and perform the SDL syntax checking and synopsis checking rule. And it will read the SDL source file. What is having given the SDL. After that, we will synopsis designer and it will check the is there any syntax error is there or not. It will check. If there is no syntax error, it will display as 1. If there is having syntax error, it will display as 0. So you have to set the syntax error. It will create the SDL object library in an intermediate file, and the intermediate file is saved in a specified location. It will create the intermediate file. If analyze report error, that must be fixed before continuing. If analyze got any syntax error, we have to fix that error first. After that, we have to move. And after the analyze, we elaborate. Elaborate is translate the design into the GTEC representation and allow the change the parameter values defined by the source code. Automatically execution of the link library here. Read file. Perform the same operation on the analyze and elaborate in one step. Does not create an intermediate file for the verilog. It will create the intermediate file for the VHDL. Define the design environments. Here we will define the design environments like operating conditions, wire load module, and a system interface. Operating conditions. These are the operating conditions are is consist of process voltage and the temperature requirements. The effect of each can be have one the chip need to be considered during the synthesis and the timing analysis. We have to check the consideration the process voltage and the temperature of the design. These are three are operating conditions. After that, wire load model. It's allow the DC to estimate the effect of wire length and fan out on resistance, capacity of the area of the net. It will allow the wire length, resistance and capacitance, and it will fan out of the resistance, capacitance, area. System interface. System interface is consist of input driving strength and the output load. Input driving sense is placed to the input port of the design, and driving sense output load is placed the output port of the design. Input driving sense is set driving cells. We will use a command for the input ports. Set load, capacity load, we will place it at the output side. Set driving cells are used to specify the driving sense of an external source that can drive an input port of the block. We are specifying the driving sense buffers that will drive the input port of the block. It is having consider we are having one design like this. Imagine in this we are having design. In this design we are having inputs like, so here it is, these two are the inputs. This here is having in these, it is one input, it is one input, it is one input. For this reason these three are the input, this is the output. It is AND gate, it is AND gate, it is OR gate. So these three are inputs here. So we will place the driving strength here for driving the input port of the block. Here we consider it is having one the, it is having our design. So it is the input ports. Here we will place the input ports. If we give the set driving cells means it will place the buffer at the near the input port of the design. After that, set load. If we are it is the output port of the design, so it will place a capacitive load. This of the set driving cells and the set load. Set load is used to place at a capacitive load at the output port of the block of the design. So it is about set system interface. Set design constraints. Design constraints are the two types. Design constraints are used to set a goal for our design, measurable circuit characteristics such as area, power, and the timing. We are setting the goals for our design like area. We have to set power. We have to meet, and the timing should be good. So, there are two types of design constraints. One is design rule constraints. Another one is a design optimization constraints. The design rule constraints the design rule constraints is optimization of maximum transition fan out capacitance and the cell degradation and the minimum capacitance. It is the design rule constraints like this: set maximum transition fan out capacitance. Set max for maximum transition we use the set maximum transition command. For the maximum fan out, set maximum fan out we will use set maximum capacitance command we will use cell degradation. For the cell degradation command we will use set minimum capacitance command we use here. Design optimization constraints. Here optimizing the design by using area, power, speed. Here is optimization with the area and the speed, power leakage. So area for optimize at maximum area. Speed means we are creating clock, input delays, output delay to the port, and timing delays. Here is optimization of the power and leakage. Optimization of the set optimization and set multi VT constraints, set leakage optimization. Timing constraints. Timing constraints are the clock, IO port, IO timing requirements, combination delay path requirement, timing exceptions. In the clocks, we are creating a clock and creating a generated clock, and clock latency we will give, uncertainty we will give, transition time we will give. The transition time is the time taken, transition time and time taken to move from low to logic, logic high to logic low. The transition time. Clock, get clocks and report clocks. These are about the clocks. Timing, IO timing. IO timings are the set input delay and the set output delays. We'll set for the timings and the combination delay. Set maximum delay and the minimum delay. For having the we are having setting the maximum delay means we will use a set maximum delay command. Minimum delay means set minimum delay command we will use. Here is a set input delay for the input ports. Output ports for the output set output delay. Timing exceptions are the set false path, set multi-cycle path. Areas, set maximum area. By setting the area, you use set maximum area. Select the compile strategy. Here we have to select the compile strategy. Like we compile strategy. Here we have select the compile strategy. The block, there are two types of those are top down and bottom up compilation. Top down compilation is the top level is the design and all the its sub designs are compiled together. Like it is a compile, it is one design, consider it is one design and it is also one sub designs are having, these are sub designs. If you do the top down compilation means it will compile all the blocks including these all blocks also it will compile. It is a top down compilation. Bottom up compilation means the individual subdivisions are compiled separately starting from the bottom of the hierarchy and proceeding up through the level of hierarchy until the top level design is compiled. And in comparison of each sub designs it will compile for first this one and another this one, after this one, after this one, and after this one, and after this one top level. Each are sub designs it will compile, each sub designs it will compile in the bottom up compilation. Mixed compilation is having the top down and bottom up strategies are whichever is most appropriate it is applied to the individual subdivisions, which is having more appropriate individuals it will apply. Mixed first it will do, and after that it is having appropriate, most appropriate this will do, and this is having most appropriate, this will do mixed, it will do mixed. Upload individual sub designs. Optimizes the design. Here the optimization, we are optimizing the design by using the compile ultra and compile. I told firstly compile ultra is if the timing is meted, compile ultra we will do. If the timing is not meted, is having some violation values. So if we give that compile ultra, the timing will be meted. So use the compile ultra is the command is gives a more effort for meeting the path which is not meeting. After that, analyze and resolve the design problems. Here we have to analyze the problem. What is the problem? If the timing is not meeting, we have to set the timing. If the check design, we will do. If the unconstrained paths are set or not correctly, we have to check. The area is correct or not, we have to check. Power is correct or not. If we are having any errors or we are having any problems, and we have to set those problems, and we have to continue. If we are having if we are in the design, we are having the unconstrained path, so we have to set those unconstrained path. And we are having a timing violations, so by using the compile ultra we can make the timing, we can set the timing, and also we can use the group paths by setting the timing. These these techniques we have to use and meet the timing. And of that area and power we have to set. After setting only, we have to save the design. Yeah, at the last step is save the design database. Whatever we get the from the design, like this, we are the timing report we will get, and we will get the area report, and we will get the power report, and also we will get the get netlist and the SG. These are main important. These are all inputs for the PNR. These two. So we will generate the netlist and the SDCs and save the database like timing, area, power. Outputs of the synthesis. These are the outputs: get level netlist, SDC, and the reports. This is SDC, and we have to save the timing and area, power values, and we will get the netlist and the HD also. We have to generate, and these by using these netlist, this netlist and the SDC, we'll design the layout or GDS form. That is physical design. By using these two, we'll go to the physical design. And here, in the physical design, also some of the inputs we have to give libraries. That is a physical design. So I will explain in details in the future classes. In each topic, we are having uncertainty, transition time, clock, generated clock, IO timings. Here is the input delay and output delay. These all will I will explain in the future classes. Thank you, everyone.